Okay, the real talk, Unit 8, acids and bases, shows up in literally every section of the AP chemistry exam. You skip this unit, you are essentially skipping your whole exam. But here is the good news, we still have more than a week. You could own this, let's make it happen. If you follow me for few videos and few minutes per video, I'm going to master this. I am about to give you 3 definitions of the same thing. Your job, know when to use each one. Get it wrong on exam day, and you lose points you didn't need to lose. Get it right, and you are ahead of 70% of the test takers. 1 week, let's close the gap. You know what kills students on the AP exam? They memorize the Arrhenius definition, ace the first few questions, then hit a conjugate, phase, pair, acid, problem, and freeze. Why? Because they never learned the pattern. Arrhenius is your starting point. It works for most lab situations. Most aqueous reactions, master it, but remember, it's a limited definition. When it fails, you will know to pull out Brønsted-Lowry. 1 week from now, we will use all 3 like a pro. But today, own Arrhenius. The acid definition produces hydrogen ions, protons, in aqueous solution. This is saying an acid is anything that, when dissolved in water, it releases hydrogen ions, the H plus. This is the identifying marker. If you see H plus appearing, you have found an acid. Example, the HCl is an aqueous solution of hydrochloric acid. It gives us H plus and Cl minus, both of them aqueous. What's happening? Hydrochloric acid breaks apart into water. Once it gets into water, it breaks apart. That's acid behavior. It spits out the H plus. Arrhenius is talking about this behavior. The chloride ion is just a spectator. It's not doing anything special. The H plus is our star. Same logic, opposite ion. A base is anything that releases hydroxide ions. The OH minus is the identifying marker. If you see OH minus showing up, you have found a base. Example, AX, the sodium hydroxide aqueous, AQ, it gives up Na plus and OH minus. Both of them are aqueous. The sodium hydroxide dissolves and releases OH ions. The sodium ion is just long here for the ride, but OH minus is doing the base work. What is the weakness of this definition? Why do we need other definitions? This is limited to aqueous solutions. It does not explain NH3. NH3 is a base, but where is the OH minus it is forming? There is no OH minus forming. So how come it is a base? That's why we need another definition. But the Arrhenius definition works great if your reaction involves water and you can see H plus or H minus ions. But what if you can? But still, the Arrhenius definition is very good. Most of the chemical reactions happens inside water. That's why the definition is not cancelled and we still use it. The Arrhenius definition connects us to the bigger picture. By understanding what Arrhenius can do, you prepare yourself to learn what Brønsted-Lowry and Lewis can do. Let's move to the other definition. Now, what does the Brønsted-Lowry definition tells us? An acid is a proton donor. So anything that gives away an H plus ion, example HCl. When HCl reacts with water, it forms the hydronium ion. Mister, what is the hydronium ion? When the H2O takes a proton, it forms H3O plus. And after losing the H, what's formed? The Cl minus. So HCl donates proton. Then what is a base? A base is a proton acceptor. Anything that accepts an H plus ion. Example, do you remember ammonia? Our problem from the last definition. NH3 and reacts with water. The water here donates a proton to the NH3. So NH3 accepts a proton, it is a base. What does it form? It forms NH4 plus. And water, after losing the H plus, it becomes OH minus. The NH3 has accepted a proton from water. That's why it's known as a base. So the advantage, this definition works in any solvent. The Arrhenius, the previous definition, required water. Here it doesn't care. You can have acid-base reactions in liquid ammonia, liquid HF, or any other solvent. The definition is about the proton transfer, not about which solvent is present. What is the second advantage? It explains ammonia as a base. This is a big fix. Remember the Arrhenius limitation? Ammonia has no OH minus, so Arrhenius could not call it a base. Brønsted-Lowry solves it. NH3 accepts a proton, so it is a base. Done. So fast summary, Arrhenius H plus and OH minus ions is our focus, while Brønsted-Lowry, proton transfer, who donates and who accepts. Requirement, water must be present. Here, any solvent, or even as a gas, no need for solvent. Now, AB chemistry, unit 8, still unit 8, conjugate acid, base, pairs, page breakdown. The definition, a conjugate pair differs only by a proton. So definition, a conjugate pair differs only by a proton. The acid gives me a conjugate base and the proton, while the base plus a proton give me a conjugate acid. So what is the conjugate base? It is what's left from the acid after it loses a proton. This is a conjugate base. What is a conjugate acid? It's what's formed after adding the proton to the base. So again, simple. You remove a proton from the acid, you form the conjugate base. You add a proton to a base, you get its conjugate acid. Example number 1, HCl. HCl is the acid. It donates H plus. What is remaining? The Cl minus. So the Cl minus is the conjugate base. It's like a friend for this acid. It's what remains from the acid after it loses the proton. So Cl minus is the conjugate base. They are a pair. They differ only by a proton. What is the difference between HCl and Cl minus? The proton. Example 2, NH3. NH3, NH3 plus H plus. NH3 is the base. You put an H plus, it forms an NH4 plus. It's called the conjugate acid. The base and the conjugate acid are a pair. They differ only by a proton. There is only a proton difference. You give the proton to the NH3, it forms its conjugate acid. They are a pair. The rule, this is exam gold. Please focus here. The strong acids have weak conjugate base. The strong base have weak conjugate acids. Why? If an acid is powerful at donating its proton, its conjugate base is terrible at accepting them back. They are inversely related. The stronger one, half of the pair is. The weaker, the other half becomes. Example, HCl is a strong acid. Its conjugate base, the Cl minus, is a weak base. It doesn't want to accept the proton from the Cl minus and go back to form the HCl. It doesn't want to do that. It's a terrible base. It does not do its job as a base. So a strong acid has a weak conjugate base. Another example is sodium hydroxide. It's a strong base. Its conjugate acid, what is the conjugate acid? What happens after it took a proton? It forms Na plus and H2O. Its Na plus is a terrible weak acid. It doesn't want to give a proton to water. But why this is important? This rule predicts the reaction direction in equilibrium problem. If you are having a strong acid and a weak base competing, the strong acid is going to win. The reaction shifts right. So strong acid moving to a weak base, the reaction shifts to the right. You will see this constantly on the AP exam. So a quick checklist. Can you identify a conjugate pair? Can you label which one is the acid base? The one that has an extra proton is the acid. Do you know the inverse strength rule? The strong one gives a weak one. The conjugate pair, the strong base gives a weak acid, and the strong acid gives a weak base. You are doing very good. Let's move on. Problem number 1. HNO3 plus H2O gives us H3O plus and NO3 minus. This is our first pair, HNO3 and NO3 minus. The HNO3 has one more proton than NO3 minus, and HNO3 donates the proton, so it is the acid. It is the one that's giving the proton to the H2O. What is left over from it is the NO3, so it is the conjugate base. Pair number 2. H3O minus and H2O. There is two pairs. So there is two pairs. This is the first pair, and then there is another pair. So the second pair is water itself with the H3O plus. So what happens? The water takes a proton. It is a base. It takes a proton from HNO3. And what happens when it takes a proton? It becomes H3O plus. So this is the base, and this is H3O plus. The hydrogen ion is the conjugate acid of this base. So I have two pairs. The clear water here acts as a base. It accepts the proton from the nitric acid, from this acid. Now, problem number 2. The NH3 reaction with the H2O to form NH4 plus and OH minus. Where is the first pair? The first pair is NH3 together with the NH4 plus. The NH3 has one more proton than the NH4 plus. The NH4 plus has one more proton than NH3. That's why NH4 plus is a conjugate base. This is the base that accepts the proton. This is the base that accepts the proton, and this is the conjugate acid. The NH3 is the base, and this is a conjugate acid. Is there another pair? Yes, there is another pair. H2O and OH minus. H2O is an acid because it donates a proton to the NH3. And what's left over from it? So the pair is what's left over. It's not the other compound. It's not the other compound. It's what's left over. You give a proton to the ammonia, and then what's left over? The OH minus. So this is a pair of this guy. So it forms a conjugate base. Who is the pair of this one? These are the one pair because what's left, what's coming after NH3 gives a proton. So in the acid we say what's left over, and in the base we say what's formed when you add the proton to it. There is always a difference of H plus between the two. There is always, so this pair they differ by an H plus, and this pair differs by an H plus. Problem number 3. HCO₃ and H2O forms H₂CO₃ and OH minus. HCO₃ minus accepts a proton from water to form H₂CO₃. This is the conjugate base. Again, this is the acid, and this is the conjugate base. You see they differ by H plus. The second pair, the H2O donates a proton. So the H2O itself is an acid. It donated a proton. And what's left over from the acid? The OH minus. So this is a conjugate base. This is a second pair. So this is pair number 2. And this is pair number 1. Pair number 1. This one and this one, pair number 1. This is the golden rule. Look for species that differ by H plus only. These are the three parts of the pair. Every conjugate pair in every reaction must follow this rule. Count the protons in each species. So here there is how many protons, and here there is how many protons. There is 1, and there is nothing. Find pairs that differ by exactly 1 H plus. So the difference between HNO₃ and NO₃ minus only lies in the proton. They differ only by this proton. This is what's available here and not available here. That's why these two are the parts of the pair. The one that has more proton, one extra proton, is the conjugate, is the acid. and the one that has less proton is a conjugate base. Again, let's have a look at NH3, NH3, and NH4 plus. The one that has more proton is the acid or the conjugate acid, and the NH3 that has less proton is the base or the conjugate base. Same thing here, NH3, NH4 plus, H2O and OH minus. H2O and OH minus differs only in H. The one that has an H plus extra is the acid, and its OH minus is the conjugate base, less proton. HCO₃ minus and H₂CO₃. The one that has an extra proton is the acid, and the one that has less proton is a base. If it is on the left side of the reaction, it's called an acid or base. If it's on the right side of the reaction, it's called the conjugate. So let me tell you this. If it is from the reactant, it's either an acid or base. If it is in the product side, it is a conjugate. It's called a conjugate. So if you have an acid and its pair, what will come with the acid? The base, but I don't call it base, I call it conjugate base. I call it the conjugate base. If I have a base on the reactant side, what comes with it? The acid. And I don't call it an acid, it's called a conjugate acid. So if you have something on the right side, it's called conjugate. If you have something on the left side, it's not called conjugate, it's either acid or base only.